Hi, this is my video entry for Electronic Systems Engineering final project. And my project was an Analogue Quadcopter Control System. For my project, mine was to mimic a digital quadcopter control system, but only using analog hardware, so not using any software. I did this by creating an analog inertial measurement unit and an analog control system. The control system is loosely based on a PID system and uses elements that I learned from Dr. John Geddes' control systems unit. This first section is for the inertial measurement unit. The inertial measurement unit has an output which is a fast responding voltage proportional triangle. It's the board that sits on the top of the quadcopter. It combines an inclinometer signal with a gyroscope signal. This is the inertial measurement unit. It is used to measure the roll angle of the quadcopter. This is done using an accelerometer, or in my case an inclinometer. These devices are susceptible to vertical and horizontal vibrations and overshoot. That's a vertical vibration showing noise, and overshoot when measuring a fast moving angle. The vibration noise can be removed using a low pass filter. However, this slows down the response of the inclinometer. So the top trace is filtered. However, it's much slower. This slow response can be sped up by using a gyroscope. A gyroscope measures angular rate, and I've integrated its output to give a pulse with the correct pulse height to sort of fill the gap of the slow responding inclinometer signal. This can be seen on screen. This is the gyroscope pulse, which is filling the gap of the slow responding inclinometer. The pulse then decays at the same rate that the inclinometer pulse edge rises. The gyroscope pulse and slow responding inclinometer signal can be summed together, and this gives back the fast responding pulses. This new signal is resistant to vibration. The inclinometer shown at the top vibrates while the bottom signal doesn't, but it also responds quickly to a roll. Okay, so let's explain some of the IMU circuitry and also how that gyroscope signal is being used to speed up the inclinometer. First of all, on the screen you can see the first bit of the circuit used in the gyroscope signal chain. The gyroscope signal comes in on C1, which removes any DC offset from the gyroscope signal. It's then amplified 10 times by U2A and inverted by U2D. These two signals are then fed to the integration circuit, which requires a differential input generated by those two op-amps. The next part of the circuit is the integration circuit. This circuit is taken from an application note on the LF298N from Texas Instruments. I've modified this circuit a little bit to improve some performance in my application. First of all, I've added two capacitors, C5 and C4, to remove any voltage offset error generated from the previous two op-amps. R26 slightly biases one half of the differential input. This means that the integration circuit will always drift towards zero instead of drifting to one of its power rails. We now have two signals which represent a voltage proportional to angle, one generated by the integrated gyroscope signal and one generated by the inclinometer. Both of these signals have varying characteristics. The inclinometer signal, when passed through a low pass filter, performs well at measuring static angles. It's good when stationary. The gyroscope version of this signal is really good at measuring rapidly moving angles. I need to be able to automatically switch between using these signals depending on the situation. During a static or slow moving angle change, I need to use the inclinometer, hence the low pass filter. During rapid changes of angle, I need to use the gyroscope signal, hence it has a high pass filter. Matching the time constants of these two filters ensures the transition occurs smoothly and dynamically between these two signals. I merge the two signals instead of switching between them. Okay, so let's explain what I mean by merging the signals. Let's take a situation where the quadcopter has rotated rapidly by 30 degrees and plot the signals outputted by each part of the circuit. Firstly, we can see the quadcopter rotating by 30 degrees and a graphical representation of this roll. This graph shows the sensor outputs for this roll. The red is the gyroscope and the blue is the filtered inclinometer, the slow response. Next, the circuit integrates this gyroscope signal. So again, the gyroscope signal shown in red and the integrated signal shown in blue. This has a drift on it, which can be seen. If this integrated signal is then passed through a high-pass filter, this signal now appears. It's important to notice that the high-pass filter version of the signal is kind of a mirror image of the slow-responding inclinometer signal, which can now be seen. By adding these two signals together, we get a very fast-responding output, which better matches the original response. This section shows the control board. The control board contains all the power management and the PD control system. I'll show a video of showing a step response and its response to interference. I'll show how I've tuned the PD system and show the thrust and control inputs. This step response shown on screen shows how I can use a power supply to supply a voltage to the quadcopter control board, which is used as a set point in the control system. I use the IMU output as a control point and use a summing amplifier to generate an error between these two voltages. If the set point is changed to 3 volts, the control system will orient the quadcopter so that the IMU outputs minus 3 volts. This will result in a negative output on the error amplifier. The error amplifier feeds the P control and I control gain amplifiers. The P, I and D gain amplifiers are simple non-inverting amplifiers. I am not currently using the I control. The P control or proportional control is summed together with the integral control and differential feedback from the gyroscope using a summing amplifier. The output from this summing amplifier forms the control signal for the motors. The motor control signal is centered around 0 volts. A positive output will turn on one motor harder and a negative output will turn on the other motor harder. To have both motors stay on while the quadcopter is level, a thrust signal must be applied. This is formed as a bias. I offset the motor control signal by the thrust voltage. Once the thrust signal is added, I now have a motor control signal, 2 of them. I've added R17 through 20 to allow for adjustments in polarity, just in case I made a mistake. The next part of the circuit is a voltage to PWM signal controller. I can input a voltage from 0 to 1 volts, which I've scaled correctly using the previous circuitry, and this outputs a 0% to 100% PWM signal, which I use then to power a MOSFET transistor and power the motors. Thrust control. I can use the power supply to generate a step input and measure the output of the Inertial Measurement Unit to judge the step response of the control board. I can use what's seen on the oscilloscope to tune the PID system. My tactic here is to increase P gain until the system overshoots slightly, and then increase D gain to compensate, and then keep cycling.